Hi, I'm Jonathan Hsueh. I'm a second year CS major, and I'm really excited to share my presentation for the ULA on the cut property. So what is this for? These are for minimum spanning trees. They are subgraphs of undirected graphs where the edges go both ways, and they have the following properties. So first, they are trees, which means they have, if n was the number of edges, they have n minus 1 edges. That is a way to minimally connect the graph. Second, they have to be connected, meaning every single node has to have a path to every other node. And then third, they can't have a cycle. If I start at one node and then I keep going across the edges, I cannot be able to, if I was able to go back to that node using a different path, there'd be a cycle. So I can't have that. And then third, the next thing is that it has to have the minimum weight edges to connect every node. A good way to illustrate that is if, let's say T is a subgraph and it is in MST, but we find T prime, which has a smaller weight than T, then T cannot be an MST. And then here's a drawing of a potential MST in the original graph. So we want to be able to find these MSTs in a graph. And let's say there's edge weights, then we want to create a minimally connected graph. So how do we do this? First of all, there's an algorithm called Prim's. It's similar to Dijkstra's, and it goes something like this. You create an array of distances, setting everything to infinity except for the starting vertex, and then you add this to a min heap. Now, starting with the node from the min heap, for every single neighbor, update the distances based on the edge weights. So if A has a path to B and that path is a weight of 3, that means B's distance is now 3. Now you want to add that minimum edge to the tree, pop the current node, and then you want to repeat this for every single node. So here's an illustration of it. I'm going to start with A, and I'm going to look at all my neighbors of A. So I see B, and the edge is 3, so now B's distance is 3. E has 3, and F has 5. So I'm done with A, and now I want to add the minimum edge, so I'm going to choose B. So I'm going to add B. Now B has an edge to F in 2, which is shorter, to G in 6, and to C in 4. Now I'm done with B, and the minimum edge here is F, so I'm going to add this wedge. Now F has a path to E in 4, and F has a path to G in 2, which is shorter. So now the shortest one, I'm done with F, is going to be G, so we're going to move on to G. Now G has a path to C in 3, which is shorter, a path to D in 8, and a path to H in 7. Now the shortest one, once we're done with G, is actually not going to be any of his neighbors. It's going to be E. And we're going to add the original edge here. Now E, unfortunately, doesn't have any other path to any other node that we haven't visited yet, so E is done. Now we're going to move on to the next shortest one, and that's going to be C. So we're going to add this edge right here. Now C has a path to D in 6, which is shorter, and then that's about it. So once we're done with C, I want to look, what's the shortest new edge that I can add? Oh my gosh, it's D with 6. So I'm going to add the edge to D. Now, D has an edge to G, which doesn't matter because we've already visited it. If we visited, that means it's longer. So, I mean, it's shorter, so we don't want to add that. But it has a path to H in 4, which is shorter. So I'm going to update this 4. Now we're done with D. Now I'm going to move on to H, and H we've already visited all of its neighbors, so that is the final distance. So this is the final tree of this algorithm. And now we're gonna move on to the topic of this, the cut property. So in a nutshell, if you have a graph with two separate partitions, if you add the minimum weight edge that spans those partitions or cut, you are guaranteed to keep the properties of an MST. Now, what does this look like? Let's say all of these edges in black are part of an MST we are building called X. And let's say we can split it up into a way that um, everything on this side is disjoint from everything on this side. And that means that there's no overlapping edges that are currently in X. However, let's say there are some edges in the original graph that span. So maybe there's one here, and there's one here. So basically, by the cut property, if you add a spanning edge only to the two disjoints, that means you're guaranteed to get a tree, which keeps the property of an MST. The second thing is, let's say all these edges have a different cost associated with them. if you add the edge with the minimum cost, let's say C1 is the minimum cost, then you are guaranteed to get an MST. So that therefore you have to add that edge. So in short, by adding a spanning edge, you ensure that you're keeping a tree with zero cycles. And by adding the minimum weight edge, then you're ensuring that it is still the minimum tree as well. So that's my presentation. Thank you so much. And thank you so much for listening. Bye. Wait, that was really good. I like that. I really like that. I like that video.